Chapter 1, Section 3, Evaluating Limits Analytically. We're going to do these first three today. Evaluate the limits using the properties, in understanding what the properties of limits are, and then develop a strategy for finding limits, and then we will get into the dividing and rationalizing techniques today. So here we go. Some basic limit properties. Theorem 1.1 says if b and c are real numbers and n is a positive integer, then what is true is that the limit as x approaches c, which is some real number, and b is some real number, it will be b. Think of this as like if I had some number 3, some real number 3, then the limit as x approaches really anything of 3 will be 3. In other words, the limit of a constant is the constant. Kind of a good one to just keep memorized. Number 2, the limit as x approaches c of x is equal to c. Basically what we're doing is just kind of replacing x. If x is moving towards c, then we can say, well then x would be c. That would be equal to c. A linear function 1-to-1. Number 3, x approaches c of the function x to the n power. We can replace x with c, and we will come up with the limit as c to the n power. There are 7 methods to evaluating limits, algebraically or analytically. And the first one is the direct substitution method. This one you want to use if you can. Always, always, always try this first. So if I have the limit as x approaches c, where c is some real number, of the function f of x, then it's going to be equal to the function just evaluated at that c value. We can just simply substitute c into the function. It will work on all polynomials, and it also works on rational functions. Rational functions, remember, like something over something, some polynomial over some polynomial, where the function is defined at c, meaning that if I plug in c into my denominator, it does not, let's say this was some value 3 maybe, and if I plug c in and c was anything but 3, it would work just fine. So quickly here, let's just use substitution. X approaches -4 of the function. Here's my f of x function. We're going to take and evaluate it by simply substituting -4 in. That's going to give us 3 then times 16, and 3 times 16 we know to be 48. Letter B. X approaches 3 pi over 4, and we want to take the limit of cosine x as x approaches that. Let's try substituting. That'll give us cosine of 3 pi over 4. Well, cosine of 3 pi over 4, if you think of your unit circle, you would be sitting over here in quadrant 2, and since it's a 45 type degree, it's going to be a square root 2 over 2 one, but we're in quadrant 2, so it's going to be negative root 2 over 2. I have a diagram or a graph that we could look at on this. Here's pi over 2, and we got pi over 2 here, and 3 pi over 4 sits between them. Notice it's down below the x-axis, or yeah, the x-axis. This would be -1, so -0.7 makes sense. And letter C, we have the limit as x approaches 10 of the square root of 6 minus x. Let's try and substitute. That would give us, I'm running out of space over in this one, 6 minus 10. That'd be the square root of -4. Yikes, that's not a real number. That's going to be 2i. And since it's not a real number and AP Calculus only works in the real numbers, we are going to say this does not exist. Here on your worksheet 2, you have the limit properties. We just went through all 3 of those. These are good ones to look at and know. So I will show these to you, or we'll talk about them just briefly. Notice that this has 2 definitions kind of in place for us. One for the limit of f of x, and 1 for the limit of g of x as x approaches c. The f function goes to L, so its limit is L, and then the g function is going to some value k. If I have a scalar multiple, so b is some real number multiplied by the function, then this b, really you could think of it as coming out front. And I would have the limit of b out front, x approaches c of f of x. Well, then it's just going to be b times, and we knew that the limit of f of x is L, so b times L. The sum or difference one, if I have two functions added or subtracted together, I can simply take each of their individual limits and add them or subtract them. The same would be true of multiplication and of division. The power function is fairly easy to understand too, isn't it? We know that we can just kind of hang on to this power function until a little later. The limit of x as it approaches c of f of x to the n power is simply going to be the limit of this f of x, which is L, and then raised to the n function. Sometimes, however, substitution does not always give us an answer. Sometimes when I substitute, especially, perhaps in a rational function, I may end up with the numerator being 0 and the denominator being 0. When this is the case, we have what is called an indeterminate form, meaning it's difficult to determine the answer, I guess. So you can think of it as that. Indeterminate forms, though, often can be solved, and we just have to find some other techniques to get around this dilemma of having 0 in the denominator, because it's difficult, isn't it? It's like, now what do I do if I have 0 in my denominator? I can't divide by 0. So we're going to be looking for techniques that get us around that problem. And one of those techniques is the factoring technique. Works really well for rational functions. What we will try to do is factor the polynomials out and then look to cancel them so that we can rewrite our original function in maybe a more simplified manner. So let me get this b out of the way. Not sure what it's doing there. And here we go. Try your hardest here. I think you'll be able to factor the top. Looks like it's an x minus 5 and an x minus 3 all over x minus 3. Looky there. You may cancel the group on top with the group on bottom, so each of those factors are removed, and that yields a much simpler form of that original rational function. It kind of boils down to just being x minus 5. So if I substitute in 3, I'd have 3 minus 5. That would give me negative 2 as an answer. We cancel this away, but if you looked at the graph of this, you would have a hole when x is equal to 3, if you remember that from last year. Letter B. See if you can factor the top. It's x cubed minus 64. Hopefully 64 is a number that rings a bell to you. It is, not only is it a perfect square, but it's a perfect cube. And this becomes the factoring of the difference of cubes. And that was something that was memorized in the last few years of your algebra and pre-calc classes. A minus b, a squared plus ab plus b squared. On the bottom one, if I had the sum of two cubes, that would factor into a plus b and a squared minus ab plus b squared. So the factoring is identical. You just have to remember where the positive and negative come into play. They each have a subtraction in them. Okay, sliding back up top, if I can get a hold of that. Now that we know that this is factorable, let's take b and rewrite it here. I'd have x minus 4 on top, and that'll be an x squared plus 4x, because it's the a times the b, and this is my a, this is my b, plus 4 squared, or 16, all over the denominator, x minus 4. I know it's just sitting down there by itself. Sometimes I think it helps kids if you write it with parentheses, because then you can see that this group clearly cancels that group. Now let's try substitution. We've kind of worked our way around the dilemma of having a 0 in the denominator when we plug in 4. So I get 4 squared. 4 times 4 is 16, and then the 16 that exists there. Looks like we got 16 plus 16 plus 16, making that 48. And C, I'm going to erase that one. C. X squared minus 225. 225, I like that number. 225 is a perfect square, isn't it? So I could really say that this is the same thing as 15 squared. And now I have a difference of squares, which is very factorable. If I were to put negative 15 into this equation, I would have had 225 minus 225 on top, so that gives me 0, and 0 on the bottom, giving me that indeterminate form. So now we're going to try and use factoring as a technique to get around the denominator issue. Difference of squares means I have one positive factor and one negative factor. On the bottom we have the positive x plus 15. Canceling the same groups there gives me limit as x approaches negative 15 of x minus 15. Use substitution now, and it looks like we'd have negative 30. Rationalizing technique. When factoring doesn't work, or if I have a rational function with a radical in it, I may want to try the rationalizing technique. So I may want to try and rationalize the function to find its limit, especially when I get that 0 over 0. This technique often works. Well, the only place I see a radical is in the denominator. So let's go ahead and try to rationalize based on the denominator. I'm going to take the square root of x, and this one had minus, so I'm going to do plus. What does that generate on the bottom? Two things that are identical except in the signs. It's like a difference of squares, isn't it? So that's going to give me just x minus 9 on the bottom. On top, I need to rationalize by multiplying by the same exact thing. So here's my rationalizing part. Now, let's write limit. The limit as x minus approaches 9. Notice how I continue to write limit over and over because it's part of the problem. Do not leave it off. On top, I certainly hope I don't have to FOIL this together because it would make a big mess. And let's just try and leave it alone, see what shakes out on the bottom. When I FOIL my bottom, I'm going to have the square root of x times the square root of x. That is x. The middle terms end up being one of them being positive, one of them being negative. They go away. They balance to 0. And then I'd have my last times my last, which is going to give me negative 9. If you want to, put parentheses around that so that you recognize that the top factor and the bottom factor eliminate each other. They cancel away to 1. That gives me the limit as x approaches 9 of the square root of x plus 3. Now let's try substitution and put 9 in its place for x, and I'd have square root of 9 plus 3. That makes 3 plus 3, which gives us 6. Letter B. So letter B. If I tried to plug in 3, I'd have 0 on the top. If I plugged in bottom, I'd have 0 on the bottom, giving me that 0 over 0 indeterminate form, meaning I should be able to try maybe a different technique and come up with the actual limit. Notice where the radicals are. They are in the bottom. So let's use the bottom as our structure to rationalize this. Square root of 3, square root of x. This one had minus, so we're going to use a plus. And we'd have square root of 3 plus square root of x. That gives me the limit, rewrite limit, of x as it approaches 3. The top would be very messy if I FOILed it. Let's just see if we can get by with not doing anything to it. Hopefully one of those terms is going to factor away. On bottom, if I FOIL, I'd have square root of 3 times square root of 3 is a 3. Middle terms will add up to 0, and then I'd have last times last, which will give me minus 3. Quick examination says this is not the same as the top. However, if I multiplied this by a negative, so if I put a negative up front, I think I can make this work. Now, I factored out a negative, so negative times negative brought me back to a positive 3. Negative times the positive x would take me back to that original negative x. So I've just rewritten this. Now let's just do, you remember doing this, I'm sure. So I have x minus 3 on top, square root of 3 plus square root of x over. Rearranging the order, I'd have x minus 3. Don't forget we have that negative out front. Now, here's a group and a group that can factor, or I'm sorry, cancel. Gives me an answer. Let's plug it in. Don't forget about the negative. I'm going to write it down right away. Negative square root 3 plus square root 3. That means I have negative 2 square root 3. Finally, last one we're going to fit in here. I see radicals in the top. That's going to be the one I am going to rationalize. If I were to put 2 in, I'd have 2 minus square root of 4. That'd be 2 minus 2. That'd give me 0 on top, 0 on bottom. This is the 0 over 0 type. Let's try rationalizing. So we'd have x plus instead of x minus. X plus the radical over x plus the radical. That takes us to the limit. Rewrite this as x approaches 2. I'd have top. Top sounds good. Let's go ahead and FOIL that out because that's like a difference of squares. So I'd have x times x gives me x squared. Minus times plus gives me the minus in between. And then I'd have radical times radical. I would not need the radical sign anymore. But I do need parentheses because I'm going to have to distribute. Don't forget we're going to end up distributing that. Negative. On bottom, I really don't want to FOIL that, so I'm just going to rewrite it as is and hope that one of these factors disappears. On top, still kind of a mess, the limit as x goes to 2. I'd have x squared, the negative 6, and negative times negative will give me positive x over x minus 2. Still got a little ways to go. Square root of 6 minus x. Well, let's try factoring the top. Is it factorable? X minus 2 and an x plus 3 should be the factoring on top. On bottom, ooh, there's an x minus 2 going to go away. That eliminates the dilemma of a 0 denominator. Switch ink here. I get those canceling. Let's try substitution. I'd have 2 plus 3 on top, making that 5. 2 go in the bottom. I'd have 2 plus the square root of 4. 2 plus 2 is 4. 5/4. Yay, we could do it. All done. We'll do homework in class tomorrow.